Hey guys, now in this video we shall see the concepts of methods of prestressing and most importantly prestress losses. Now let's start with the first question. In case of post tensioning, the prestress is imparted to concrete through. So how the prestress is imparted to concrete in case of post tensioning? We have two things like pre-tensioning and post tensioning. Here in this question they have mentioned post tensioning. So in the case of post tensioning, how the prestress is imparted to concrete. Here the option correct is option A, bearing. So through bearing we can impart prestress to post tensioned beam or the post tensioned concrete beam. Now let's see how that will be imparted in case of pre-tensioning. In case of pre-tensioning, we can impart prestress to concrete through bond between steel and concrete. Here steel refers to the tendons or wires that is used for prestressing. So bond between steel and concrete will impart the prestress to the concrete in case of pre-tensioning. So that's why it is called as bonded prestressed concrete. And in case of post-tensioning, as we have already seen, this is done by bearing. So that is why it is called as non-bonded prestressed concrete. Now let's see some more points regarding concrete and steel material. Why we have to use high strength concrete and why we have to use high strength steel. First, let's see the high strength concrete concept. So high strength concrete has to be used because the Young's modulus of elasticity of that high strength concrete will be higher, because you can see here the formula E is equal to 5000 root FCK, where FCK is the characteristic strength of concrete. If we are using high strength concrete such as M50, M60, then Young's modulus of that concrete will be higher because E is directly proportional to characteristic strength of concrete. So Young's modulus of elasticity will be higher for high strength concrete. But why we have to use? We can reduce elastic and crack strains. So that will result in the smaller loss in prestress. So in order to lessen the prestressing force, we have to use high strength concrete. And by using high strength concrete, we can reduce the size of the concrete sections. We can reduce the size of the concrete beams like that. So we have to use high strength concrete in order to mitigate the losses in prestressing force. Similarly, we have to use high tensile steel. High tensile steel has to be used with initial prestress, which ranges from 1000 to 2000 megapascal or Newton per mm square. So why we have to use high tensile steel? Because prestressing force will have a loss of around 10 to 15 percentage. So in case we are using mild steel or like that, that loss will get accommodated to that yield strength of the steel. So that's why we have to use high tensile steel in case of pre-stressing concrete, because high tensile steel have initial pre-stress in steel which ranges from 1000 to 2000 Newton per mm square. And the properties of high tensile steel as follows: 0.6 to 0.85 percentage carbon. That steel or tendon material should contain 0.6 to 0.85 percentage carbon and 0.7 to 1 percentage manganese, 0.05 percentage sulfur and phosphorus. This point is somewhat extra thing. We have to remember this carbon percentage alone. 0.6 to 0.85 percentage carbon has to be there as a composition in case of high tensile tendon or wire. For high tensile wires, the Young's modulus will be 210 kilonewton per meter square. And in case of high tensile bars, Young's modulus shall be 200 kilonewton per meter square. In case of strands, we have Young's modulus as 195 kilonewton per meter square. We have many forms of high tensile steel. In case of pre-stressing, we have wires, bars, strands, tendons, like that. So accordingly, we have to choose the Young's modulus so that we can calculate the modular ratio and upcoming calculations. The minimum percentage of elongation for wires shall be 2.5 percentage. In case of bars, it shall be 10%, and in case of strands, it shall be 3.5%. These specifications and these rules are provided by IS 1343 codal provisions. The helical form of wires improves the bond strength. This is an important point. Uh, Helical form of wires can improve the bond strength. So that means what? We can use helical form of wires in case of pre-tensioning, because we have already seen pre-tensioning For pre-tensioning, the pre-stress is imparted through the bond between steel and concrete. So by improving the bond strength, we can provide a high strength pre-tensioned concrete. So that's why we have to use helical form of wires in case of pre-tensioned concrete. So that will fetch us a good material. And now next is the relaxation in steel. What is the relaxation? It is the decrease in stress in steel at a constant strain. This point has to be noted. At a constant strain, there is a decrease in stress. So that is known as relaxation in steel. These points will be important to calculate the losses in pre-stressing concrete. That we'll see in the next question. This question deals with the tendons. Curved tendons cannot be used in. Actually, this question deals with the methods of pre-stressing. So, in which method we cannot use curved tendons, whether it is Magnell Blatten system, whether it is Gifford Udall system, or Lee McCall system, or Hoyer's system. So, we have many systems for pre-stressing that we shall see now after getting the answer for this. So here curved tendons, where we cannot use curved tendons, in which system we cannot use curved tendons. The answer is option C, Lee McCall system. In Lee McCall system, there is a disadvantage. That is nothing but we cannot use curved tendons. We can only use the straight tendons. Now we shall see one by one the systems and what are the advantages. For pre-tensioning system, we are using Hoyer system. For pre-tensioning the material or pre-tensioning the wires, we are using Hoyer system. In Hoyer system, you can see this uh, schematic representation. These are the concrete beams, and it will be lined together. And this is the tendon. This red line is the tendon or the group of wires, and here the pre-tensioning occurs. After tensioning, the concrete is poured. So that is the pre-tensioning. Pre-tensioning means first the tendons will be pulled or tensioned. After that, the concrete will be casted, and after casting, this jack will be removed. So that is the pre-tensioning system. Now we shall move on to post-tensioning. How post-tensioning can be done? It can be done by using wedge action or direct bearing or looping wires around the concrete. So these three methods we can use for post-tensioning system. And in case of bearing action, Lee McCall system can be used. So here you can see in this diagram, this is the Lee McCall system. In this is a high tensile rod, and here a bearing mechanism will be there using some kind of mechanism that will be followed in Lee McCall system. We can just know we can just be aware that Lee McCall system is based on bearing action. Similarly, for wedge action, we can use Fresnel system. In Fresnel system, we are using large number of wires that can be tensioned simultaneously. You can see here. This is a group of large number of wires or tendons that can be tensioned at the same time, or we can say simultaneously. We can tension such a large number of wires in Fresnel system. Similarly, we have Gifford-Udall system. In this system, wires can be tensioned separately, not in together. Here you can see the schematic representation. This is the tendon high tensile wire, and this is the setup in case of Gifford-Udall system. In this, each wire has to be tensioned separately. And next is the Magnell Blatten system. Here, two wires stretched at a time. This is the setup, actual setup for Magnell Blatten system. Here, two wires are stretched at a time. So these three are corresponding to wedge action, and Lee McCall system is based on bearing action. And for pre-tensioning system, Hoyer system. That is, first we have to tension the tendons, and after that concrete has to be poured. But in case of post tensioning system, everything has to be casted, and in the duct that we have provided for tendon, after casting the concrete, the tendons will be tensioned. That is called post tensioning. So this is about the systems of pre-stressing. Now let's move on to the next question. In the next upcoming question, we shall see the losses, how to calculate the losses in prestress. So consider the details for the next two questions. You can pause this video and write down the points, write down the given data, so that for the upcoming question we can you can refer the data to solve that question. So by using the previous data, we can calculate some things like cross-sectional area of the beam section, moment of inertia BD cube by 12, initial prestressing force, that is nothing but initial stress into the area of tendon or the area of high tensile wires, that is used in this problem. And modular ratio is the Young's modulus of steel divided by Young's modulus of concrete. This data already given, so upon substituting we can get the answer for modular ratio as 6. And stress in concrete at the level of steel, that is the this, like F suffix C is equal to P by A plus PE by I into E. Here E is nothing but the eccentricity, and we have assumed here as the uniform eccentricity throughout the section. So P into E is nothing but 50 mm divided by I we have found, P we know what is P, that is pre-stressing force 414 kilonewton, and A is the area of concrete beam, that is 215 to 400, that is 10 power 5 mm square. So upon substituting the values here, we can get the answer for FC as 4.9164 Newton per mm square. That is nothing but the stress in concrete at the steel level. Now we shall see the question. Find the percentage loss of stress in wires if the beam is pre-tension. So consider all the data and the calculation that we have already done before this. So by considering all the data, we have to find the percentage loss of stress in wires in case the beam is pre-tensioned. When the beam is pre-tensioned, we have some set of losses that we have to consider so that we can find the percentage loss of stress, that we shall see now. Here the option D is correct one, 17.09. Now let's see one by one how to calculate, what are the steps we have to follow. First, let's see what are the loss to be considered in case of pre-tensioned beam. In case of pre-tensioned beam, we have these losses: elastic deformation of concrete, loss due to creep of concrete, loss due to shrinkage of concrete, and loss due to relaxation in steel. So how many? 1, 2, 3, 4. So 4 losses are there in case of pre-tensioning of the concrete beam. Now let's see the calculation of one by one. So first let's see the elastic deformation of concrete. Loss is equal to M into FC. What is M? Modular ratio that we have already calculated in the previous slide, that is 6. FC is the stress in steel level, that is calculated as 4.9164. So multiplying both the things, we get the answer as 29.5 Newton per mm square. So this is the loss in loss of stress in wire due to pre-tensioning, due to elastic deformation of concrete. And now let's move on to the creep of concrete. Due to creep of concrete, what is the loss? So loss is given by epsilon into FC into ES. What is epsilon here? This is the creep strain, or we can say ultimate creep strain as given in the data. For pre-tensioning, we have ultimate strain given as 45 into 10 power minus 6 per Newton per mm square. So into FC is, we have found FC as 4.9164 into ES is nothing but Young's modulus of steel. Here they have given us 210 kilonewton per meter square. So upon substituting the values, we get the loss value as 46.5 Newton per mm square. So this is the formula regarding the loss due to creep of concrete, that is epsilon cc fc es, that is the ultimate ultimate creep strain in case of pre-tensioning, and fc, that is stress in steel level, into es is the Young's modulus of steel. And next we shall move on to shrinkage, loss due to shrinkage of concrete. So that is given by shrinkage strain into elastic modulus of steel. So shrinkage strain for pre-tensioning shall be assumed as 3 into 10 power minus 4 into ES, that is 2 into 10 power 3. So multiplying these two things, we get 63 Newton per mm square as the loss due to shrinkage of concrete. And next is the relaxation, loss due to relaxation in steel. So they have given loss due to relaxation in steel as 5%. So that is nothing but 5% of initial stress. So 0.05 into initial stress is given as 1150. So 0.05 into 1150 gives 57.5 Newton per mm square. So we got all the four values in case of pre-tensioning. Four losses 29.5 and 46.5 and 63 and 57.5. So adding all the things together, we get total losses 196.5 Newton per mm square. So adding all the four losses, we get total loss value as 196.5 Newton per mm square. And what is the percentage loss? So total loss divided by the initial pre-stress, that is 1150. So this is the percentage loss 17.09% in case of pre-tensioning. In case of pre-tensioning, we are considering elastic deformation, creep of concrete, shrinkage of concrete, relaxation in steel. These are the important things regarding loss in pre-tensioned beam. Here one thing has to be noted. This creep of concrete loss is given as epsilon cc fc into es. This formula is used in case we are given ultimate creep strain. There is another formula regarding creep coefficient, that is nothing but m phi into fc, that we shall see in the next question. Now we shall move on to the next question for post tension. Find the percentage loss of stress in wires of the same data given in the previous slide if the beam is post tension. So we see the calculations and what are the losses that we have to consider in case of pre-tension the beam. In this question they have mentioned post tension. So what are the percentage, what are the losses to be considered in case of post tension beam? That we shall see now. Here the correct option is option D, 14.48%. So here, what are the losses in post-tensioned beam? Here also we have to consider creep of concrete, shrinkage of concrete, and relaxation in steel. But there is no elastic deformation. We should not consider elastic deformation in case of post-tensioned beam. We have to consider these two things: anchorage slip and friction. Loss due to anchorage slip and friction. So here we have 5 losses, but we have to consider elastic deformation of steel in case many tendons are simultaneously tensioning. So that is a different case. But by now we can restrict up to these 5 things. In case of post-tensioned beam, we have to consider the 5 losses: creep of concrete, shrinkage of concrete, laceration in steel, anchorage slip and friction. Now we shall move on to calculation part. First we shall see how to calculate the anchorage slip. Due to anchorage slip, what is the loss? Loss is equal to ES into del by L. What is del? Del is the slip value. They have given us some 1.25 mm if I remember correct. So ES is the Young's modulus of steel into del is the slip value divided by span. Span is the that is nothing but the length of the beam. So upon substituting all the things with relevant units, we get loss value as 26.25 Newton per mm square. And we shall see now the friction. Due to friction, what is the loss? Due to friction, loss is given by nu into alpha plus kx into initial stress. We have been given like k value. We don't have values of nu and alpha. Nu is the coefficient of friction, alpha is the angle of friction, like that. So we don't have this nu and alpha thing. So that's why we can neglect that. We can only use kx value. What is k? K is nothing but the coefficient of wobble effect, that is given as 0.0013. So we have k value. What is x? X is the span of the beam. We have span of the beam as 10 meter. So 0.0013 into 10 into the initial stress. What is initial stress? 1150. So we know k, x and initial stress. So upon substituting all the things, we get the loss due to friction as 14.95 Newton per mm square. This is the main important thing regarding a post tension beam. We have to consider anchorage slip and friction. And similarly, we have to consider creep of concrete, shrinkage of concrete, and relaxation in steel. The same approach has to be followed as we have dealt in pre-tensioned case. So loss is given as this formula: shrinkage epsilon shrinkage strain into ES, relaxation in steel, percentage of initial stress. Here the value is different because in the given data they have given a separate value for post tension case. So that's why 2.15 into 10 power minus 4. So upon adding all the losses, we get total losses 166.55 Newton per mm square. So what is the percentage loss? 166.55 divided by 1150. That gives answer as 14.48%. So we have seen percentage loss in case of pre-tension and percentage loss in case of post-tension by using the same data. So these are the important things regarding losses in pre-stress. Now we shall move on to the next question. A concrete beam is post-tensioned by a cable with a pre-stressing force of 450 kN. So here they have mentioned the pre-stressing force, and the area of cable wires is 150 mm square. We have to find the loss due to shrinkage of concrete alone. They have given the value of ES and the age of concrete at transfer is 8 days. So we have to clearly note that the pre-stress method is post-tensioning, and we have to calculate only the loss due to shrinkage of concrete by using the given data. Here the option is option B, 1.4 percentage. So this is the formula for force post-tensioned beam. Total residual shrinkage strain is given by 2 into 10 power minus 4 divided by log of T plus 2. Here T is the age of concrete at transfer. Here they have given as 8 days. So log of 8 plus 2 is log 10. Log 10 is 1. So that's why shrinkage strain is nothing but 2 into 10 power minus 4. Then what will be the loss of stress due to shrinkage strain? That we have already seen in the previous question. That is nothing but shrinkage strain into the elastic modulus of steel. So 2 into 10 power minus 4 into 210 into 10 power 3 gives the loss due to shrinkage strain, and that loss divided by the initial pre-stress. What is the initial pre-stress here? Pre-stressing force is 450 kN and area of cable wires is 150 mm square. So dividing these two things, we get the initial stress, and we have already calculated the loss of stress due to shrinkage strain. Divide both the things to get the answer for loss in percentage. That is 1.4 percentage due to the shrinkage of concrete in case of post tension. And now we shall see now more important things regarding shrinkage strain and other things. This shrinkage strain value should not exceed 3 into 10 power minus 4. In case of pre-tensioning, we already assume that the shrinkage strain shall be 3 into 10 power minus 4. But in case of post-tensioning, we are using this formula. Even though we can use this formula, this value shall not exceed 3 into 10 power minus 4 strain. This value is the maximum strain that we have to assume or adopt. And in case we are using graphite in the post-tensioning duct, that gives the lowest value of friction coefficient. So by using graphite, we can reduce the loss of pre-stress due to friction. So that is the concept here. And we already mentioned like a creep coefficient. In the previous question, we used ultimate creep strain. But here another thing, creep coefficient is that. By using creep coefficient method also, we can use or we can find the loss due to loss due to creep of concrete. So here loss is equal to m into 5 into fc. M is modular ratio, phi is the creep coefficient value, fc is the stress at steel level. So by using this formula, we can calculate the loss due to creep of concrete. This creep coefficient value varies from 1.5 for wet situation to 4.0 for dry situations. So in this video, we have covered the losses in pre-stress, how to calculate the losses in case of pre-tension beam, in case of post-tension beam, and what are the methods and the systems of pre-stressing, pre-tensioning, and post-tensioning. So that's all about this video. If you like this video, please like, comment, and share with your friends. Thank you for watching.